Hi guys. So the purpose of this tutorial is just to show you guys how I use Mnova to analyze my NMR spectra. One of the first things I like to do is make sure that my pages pane here is open. If it's not, go to view and make sure that the pages option is selected. You may have more than one spectrum to analyze at a time, so it's nice to have them all listed here. The next thing I like to do is ensure that I have a view to my entire spectrum and that none of the chemical shifts are cut off. It does look like that some is cut off because it's not starting from zero and there might be peaks over the range too. So I like to use this tool here, the full spectrum. The short is the letter F on your keyboard. So I'm just going to press that and make sure I have um, a, a full spectrum view. Once that's done, I like to cut off any of the extra regions where I don't see any peaks. For that, I use the cut tool here, or alternatively, you can use the short, which is X on your keyboard. And it literally just works like a scissor, and you can cut off the unwanted regions, and it just makes it more easy for you to work. In order to get rid of the scissor sign, you can press escape or just go down here and just select the select option to go back to your cursor. So I'm just going to press escape. Okay, now once that's done, I usually like to play with my aesthetics first. So I like to make it look a little um, more neat. So one of the first things I do is double click on the spectrum and check off the title, which is this here. I don't want it. And also for the grid, I check off all the background. So apply, okay. So that's neat. In order to play with the intensity, you can just scroll up or down on your keypad until you get like a reasonable intensity. So you can also adjust the y-axis. Let's say, for example, after we do integration, you're going to see numbers down here. And if for some reason those numbers are appearing on top of your peaks, you can always adjust the height of your peaks. That's pretty much it for the aesthetics. The first step in your analysis should be identifying your solvent peaks. It just makes it easier. So what I usually like to do is use this peak picking tool. You can directly click on it and it's going to pick all the peaks, or you can click on it and click automatic, which is also going to do the same thing. And the reason I do this is to identify what solvent was used. Sometimes it says in the title, which was up here a little while ago, what solvent was used, but sometimes it doesn't. So this is always a good way to find out. So it looks like we used DMSO, and DMSO is often accompanied with some water. So those two peaks you can confidently say are not coming from your product, and so you won't start integrating them or anything. So first step should be assigning or yeah, assigning a reference peak, which is usually the solvent. So for that, I would first zoom in on my solvent peak. For that, you can use this magnifying glass here, zoom in button, or I just press the Z key alternatively on my keyboard, and I just zoom in. So as you can see, it looks like a multiplet. So first thing you do is find out the chemical shift of your solvent. So I know from experience that DMSO does come out at 2.5, but it could be a different solvent. And if you haven't worked with DMSO before, you would need that information. For that, you would consult this paper that has been posted on Quirkus for you. That's the title there. All you need is to look at this first table number 1 here, and basically the first row. So you're looking for the residual signals that your solvent may produce in the spectrum. So these are some of the common solvents that are used. The one we used is DMSO, so it's deuterated, that's why it's CD3 2SO. And as you can see, the signal is indeed 2.5 ppm. Now let's say this is just an example. I think I've already analyzed this data before. That's why it's set at 2.5. But most times, like I'd say almost 99% of the time, it wouldn't be coming out at 2.5. It would be slightly off, either 2.49 or 5.1, anything like that. You still have to go and edit it and set it to exactly 2.5. I'll just show you how to do that. So let's go back. What you do is you right click, reference, reference, or you can just select the L key on your keyboard. It's not going to pop up anything, but now you can basically pick the peak. So I usually like to pick the middle peak and set the new shift as your desired shift, which is 2.5 in this case. So we are not really changing anything. And just press OK. So now you've selected your reference peak. Now in order to zoom out, I just either you can go to the full spectrum tool up here, or just press the F key on your keyboard. Okay, so once that's done, I'm just going to remove the solvent labels. In your final spectrum, you shouldn't have any of these red labels for the solvent. I'll show you how to indicate any of the solvent peaks. So for now, I'm just going to go to the peak picking option and delete manually the solvent peaks. Even this little guy here looks like an artifact, so I'm just going to remove that too. There is no peak there. So the peak labels should only be for your actual peaks, actual product peaks. Okay, to get out of this cursor again, I'm just going to press escape. Okay, so once this is done, the next thing that you should do is go to ChemDraw and draw your structure out. I'm working with a molecule called Dulcin, and predict its NMR shifts. So it kind of guides you on what you're looking for in your actual compound. And then if you have anything extra or anything missing, you can talk about that in your lab report. So first, I'd like to explain what the integral will give you, because the first thing that we're going to do is integration. So let's say if I integrate this peak here, which I believe corresponds to this one in our actual spectrum, that's coming out at around 1.5 ppm, and so is this one. So when I hover on top of this peak, you can see that a green box also gets selected here, and it works vice versa. So it's telling you that this peak is coming from these two protons, or in other words, these two protons three protons, because it's a CH3 here, are experiencing this chemical shift. So I would say the integration of this peak would be 3. For this guy here, it's coming from those two hydrogens, right? So it's a CH2. So I would say that the integration for this peak here is 2, and so on. So it's important to understand what integration means. It's basically the number of protons that are experiencing that chemical shift. So usually you have to pick a peak in your spectrum every time that you are almost sure of that how many protons it's coming from. So usually a rule of thumb is that you pick the CH3 peak because it's the least de-shielded one, right? Usually comes out between 1 and 2 ppm, and you can almost confidently say that it's a CH3 peak, so we can use that as our starting point. Remember, you should always have a starting point, and then everything that you integrate from that point onward is with reference to your starting point. So you have to be sure of your first peak. So now at this point, I can confidently say that this peak here in my actual spectrum is actually this one here, which corresponds to the CH3 peak. So I'm going to go ahead and integrate. I'm going to start with this one, and I'll show you what happens. Okay. Now, in order to integrate, first I'd like to zoom in on it. So just press the Z key. And to integrate, we literally use this symbol that has the integral symbol on it. So you can click on it, and this time we only do manual. Again, the alternative is to just press the I key. So you'll go to that cursor, and then you just drag over your peak. So we just looked at the predicted NMR, and we saw that this peak should actually have an integration of 3 because 3 protons are experiencing it. But this is just something that Mnova does. The first integral that you pick, it's always 1. So it's your job to edit it. So that's why you pick a peak that you're sure of. Like for this one, I'm sure that this is a CH3 peak, so I'm going to edit integral, and I'm going to set it to 3. And now everything onward should be correct if this is correct. So now I'm just going to zoom out. So press the F key. Now I'm going to do the same thing. So again, these two we decided were our solvents, right? This is DMSO and this is the water. So we're going to skip them. We're not integrating them. I'm going to go ahead and integrate this peak here. So if you want a closer look, I'm just going to zoom in and show you. So yeah, that looks like a little bit of an overkill. So if you've made a mistake, if it looks like you've got covered way too much area, then get out of the whatever cursor you're at and right click and you can delete integral. And then you can repeat. So I'm just going to press the I key and maybe go a little closer. Yeah, so it's pretty close. So 2.03. So you can round that down to 2 ppm. And now we're going to go back to our predicted NMR and see if the second one was actually 2 ppm. It is. Oh, sorry, not sorry, 2 ppm. The integral is 2. So if you hover over this, you can see that it's actually coming from 2 protons, right? So looks like so far our integration is going fine. So now we're going to continue and just keep zooming in on the remainder of the peaks. So okay, so let's integrate all of them. So this one, it's saying it's 1.96, can also be considered 2. These look like our typical para-substituted benzene shifts, and that looks like an NH peak. So once that's done, you can compare again with the predicted NMR. So, oops, sorry. Okay, so this one here is our third peak, and as you can see, it is indeed coming from 2 protons. So 1.96 is 2, and again, you just need to look at the NH2 here. So that makes sense. The next one here is coming from those 2 protons, the benzene protons or the phenyl protons, and same here. So everything makes sense. All the integrals are matching, and this last one here should have an integration of 1 because it's only 1 NH proton, and let's just see. Yeah, that's the case. So 0.96 is very close to 1. So this has just confirmed that our integrations were correct, and it already confirms that we most likely made our product. Don't forget the purpose of all these characterization tests, NMR, IR. They're there to confirm if you made your product or not. So in your lab report, make sure you use that type of language where you say according to the chemical shifts or according to the NMR spectra and figure, blah, blah, blah. Just try to support your findings. Okay, so I'm just going to zoom out. So our integration is done. The next main step is what's called multiplet analysis. So multiplet analysis basically gives you your coupling constants, right? Also tells you if it's a singlet, doublet, triplet, multiplet, and all of that information. So the way I do it is I do the multiplet analysis, but then it makes the spectrum very crowded, and most TAs do not like it. Again, I would suggest that you speak with your TA if they want you to do leave the multiplets on the spectrum. I'll show you in a second how they look like. But the way I'm showing you has been working very well for me as a student, so I would just use this. So for multiplets, you go to this little J icon here, and again, you click on manual. So alternatively, press the J key. I would get used to these shortcuts. It just makes your work a lot faster. So once you've selected that, it works very similar to an integral, except that it starts off at 1 as well. So I'm just going to zoom in here to show you. So if you notice, it's still starting off as 1, but since we're not bothered by it, we're not doing this for integration. We're doing it just to get our multiplets, our coupling constants. We're not going to stress ourselves with correcting that to 3 and then integrating again. You can do that, but you don't have to. So I would just zoom out and literally, I'm going to press the J key and go and do the multiplet analysis blindly on all of them. Here you don't have to worry about the number that's showing because we're going to delete that anyway. And now you see how ugly it looks. It looks very crowded, very messy, and you're automatically going to lose some marks if you submit it like this, right? There are ways of hiding these integrals if you want. I can show you guys. For example, you can double click on the screen. If you go to integrals, you can check off this labels and curve. Curve means this integral curve. You can do that. You can do the same thing for multiplets. So the purple ones can also, you can make them disappear. But don't bother with that. It's okay to keep one set, but we're going to remove the other set in a bit. Okay, so we finished our multiplet analysis. Right now, it's not giving you any information other than the fact that the T here is telling you this is a triplet coming out at 1.29 ppm. It's reading off the x-axis basically. Again, these are multiplets, they're singlets, and so on, right? But we want this information more concise in a table, in a text box. So for that, you go to the multiplet tool again here, and you say report multiplets. So this is the most important part, I'd say, of the analysis. Once you do that, it generates this text box for you. So once you guys have access to your lab report template, you're going to see that the professor expects you to report all your data in this form. So it tells you the frequency of your magnet that was used for the NMR, the solvent that was used, so deuterated DMSO. It gives you your chemical shifts. And now if you notice, the hydrogens are off. These hydrogens are what should be coming from your integration, right? So the entire purpose of doing this multiplet analysis was to get to this text box. Once you've gotten to it, delete your multiplets. So just go to the J here and say delete all. So now they're gone. You can adjust the height of these integrals here, make them look nice. And next thing you have to do is edit this text box according to your actual integrals. For example, so I'm just going to click on it. You can double click on it to start editing. So it says that the chemical shift at 8.28 ppm, which is this one here, it's reading that as 0 hydrogens. You know it's not 0, it's 1 according to your integration. Then between 7.5 and 7.05, which is this one here, it's 2 protons. So you fix that as well. And same thing here, it's 2 protons. And the next one here is 1 proton. This guy here is also 2. So now you see it also gives you the coupling constant, the J value. So if you remember, the J values are for, I believe, I'm not sure if they're for doublets or not, but they're definitely for, yeah, there should be some for doublets, triplets, and so on, but you don't have them for multiplets or singlets. So here, 3.94 is this one, so it's 2 protons, and the last one needs to be corrected to 3 protons. So we'll talk in a bit how you can ensure that you got the correct compound just by looking at the number of protons. So yeah, you can adjust the size of this, make it look nice however you like. So we're almost done. Another important thing, very, very important thing that you should do is expand the peaks that you think are important but are kind of not as clear. For example, by looking at this, I cannot tell that it's experiencing that it actually has 4 peaks, right? Similarly, for this one, I cannot even tell that it's a triplet until I zoom in. So give your TA that information. And how you do that, you basically use this tool here called the expansion. You click on it, and it literally expands the region for you that you're interested in. So you see how it generated this ugly spectrum on top of your spectrum? So just drag it over into a clean place, and you can play with it. You can hide its own axes so that all you can see is the peak, just a little more visible, and also the integral that's coming can be deleted. Delete integral. These peaks here can also be deleted. I'm sure there's a way to delete them all together, but I just and select them, I guess. Okay. So now it's clean. You can, again, use your mouse pad to scroll up, right? And you can use the cut tool that we used previously to get rid of that extra region. We don't want that. And you can get rid of this, make it a little tall. Overall, reduce the size and just put it right on top of the peak that you just expanded. You can cut off a little more too. If that looks too wide, you can just make it a little skinny and it serves the purpose, right? So now your TA can tell that, okay, there is indeed a triplet there, right? So every time you think you need to provide more clarification, do so, as far as you're not making your spectrum look too untidy. You can do the same thing for this one. Feel free to skip this part because I've just shown you how to do it. So again, right click, check off the show part, and then delete integral. How do I delete? I can keep this selected. I can still use the peak option here and say delete all. There. So now again, I'm going to scroll up, cut all the extra parts. Okay, and then just make it a little skinny. Perfect. Okay, so now that's done. I don't think you need to do it for the benzene peaks because that's pretty understood. That's common knowledge, right? That benzenes have those typical chemical shifts and the multiplets. All right, so once that's done, the next thing, the very important thing that we still have to do is put our structure onto the spectrum. So the way you do that, you just go to your ChemDraw, you've already drawn it. So usually you can copy it directly. For some reason in this old version of Mnova, I cannot copy it directly onto my spectrum. I always have to paste it on an empty Word document first. I'm sure this is not, it was just a glitch with this version, and if you're using the latest one, you should be able to paste it directly here without having to go to, actually I also have to resize it here. If I resize on Mnova, it's a big mess. So, oh, sorry, another thing, if you're using the ChemDraw that gives you the numbers, the atoms for you, that's not good. So make sure you unnumber them. So how do you do that? Atom, show atom number. No. Okay, so check that off. So yeah, you don't want any numbers on the atoms because you're going to do that manually. I'll show you how. So okay, that's a good size. There. So now it's up here. You can decide how to organize really as far as it looks neat. Okay, and this can come a little down. All right, so now what you do next is you number your protons or your peaks. So I'm just gonna use the text box here and call this 1. So I kind of like to make it very neat. So since it's coming in my way, I'm just gonna move it a little up. I can make it smaller too. Okay, and the peak can go right on top. The number can go right on top of the peak. Yeah, sometimes it's a mess. Okay, and then I'm just going to keep pasting this. And this is my peak 2. So the next thing you do after numbering all of them, you're going to copy these same numbers onto your structure up here and number your protons. You're basically labeling them. and telling your TA which peaks correspond to which protons. And for example, if you see an extra proton or extra, sorry, peak, you have something to talk about in your report. There could be a possible impurity that's giving rise to those peaks. Okay, so once you've numbered them, don't forget to label your solvents. So as we saw earlier, this is our DMSO. And this here is our water. Okay, so everything's been labeled. I'm just gonna, so you can look back to your predicted NMR to find out which protons were really causing these shifts. But since I just did it, I remember that this was our CH3, so those are the protons. For peak 2, it was these protons here. Oops, sorry. Peak 3 was, it's 2 doublet. I believe it was these two protons here. So again, if you're not sure, just go back to your predicted NMR and double check. Sorry, this is 3. Number 4 were these two. So this time it's coming from, so two different, one proton here and one proton here are experiencing this shift. And then the two protons here. Okay. And then lastly, number 6 is the one NH proton here. Okay. So if you want, honestly, you can make the structure a little bigger. That's a little too tiny, but it serves the purpose, and it looked too stretched out. Okay, so I believe we have almost everything. We've numbered it. I'm just going to come a little down. I believe that should be all. Just going to close these extra things. Oh, you see, if I move the structure up or down, it kind of moves everything. So yeah, another thing I wanted to tell you guys is when you're labeling your peaks, make sure you're not zoomed in. So don't zoom in on this and then put 1, because when you zoom out to your full spectrum, the numbers will be all over the place. So start labeling only when you're ready. Don't zoom in on anything to make a label. Also, oftentimes you will see random peaks. If you're able to identify those peaks as known impurities, for example, ethanol or something like a starting material, for example, the more characterization you can do, the better. If you just label it as an impurity, that's not really, it'll still get you the marks that at least you didn't leave it unlabeled, but there will be students who are very, very good at characterization. For example, I can help you guys by showing you this table here. So one thing that you can take a look at is that um, think about different solvents that you use during your purification process. For example, in the case of most recrystallization experiments, we use ethanol as our solvent. So there is a chance that you might get ethanol, an ethanol peak in your spectrum, right? How do you identify it? I would look at CD, so I would just focus on this column here, go all the way down, find ethanol on this side here, and just see, okay, so at 1.06 in DMSO, in DMSO, the ethanol shift is at around 1.06. And then you go back to your spectrum and you see if you see something at around that ppm. Right now we don't. So, and this product wasn't actually recrystallized in ethanol. So that makes sense, but there is a very high chance that you might see ethanol. That's actually one of the most common impurities that I've seen in my experience. So if you see that extra peak here does not match with any of the protons in your compound, then don't just label it impurity. You can, but make sure you talk about it in your discussion, right? Or you can even label it here that it's possible ethanol and explain, cite this paper, give reference to this paper and explain that in DMSO, ethanol comes out at this chemical shift, hence I can confidently say that it's ethanol and things like that. Try to make your claims very strong, and I think that's going to help you get a good grade. Other than that, oh, for your final lab report, there will be a table asking you to report the multiplets. For that, you just copy this table on and this little text box, and that should be it. Now, to save this, you can, I believe, save it as, you can export to PDF, or you can also, I believe, save as an image file, and then, yeah, JPEG, and you just paste it onto your report, and that should be good. I would like to thank you all for listening, and all the best.